Welcome. We will do two sections together with this screencast. The first section is 14J, probabilities from Venn diagrams, and it's going to be very short and it's going to rely on what we learned a couple of weeks ago. So the objective is simply to use Venn diagrams to find probabilities. So here's an example of what we're talking about. In a class of 20 students, 15 study chemistry, 9 study history, and 7 study both. Draw a Venn diagram and determine the probability that a randomly selected student A, B, C. So firstly, we need to remember how to draw Venn diagrams. You see that 15 people study chemistry and 9 study history, therefore 15 plus 9 equals 24. Obviously, some students are listed both as studying chemistry and studying history. So when we do Venn diagrams, we want to start in the middle if we can. And here we know that 7 study both, so we'll put a 7 in the middle. And that means there are 8 students left who do not study history. So here it is, here. And likewise, since 7 people study both history and chemistry, that means only 2 students study history only. And finally, we need to double check how many students we now have together. 8 plus 7, 15 plus 2, 17. So there's also 3 students who study neither chemistry nor history. And once we have that, it's easy to answer questions A, B, C. What is the probability that a randomly selected student studies chemistry? There are 15 students who study chemistry out of 20. So the probability that that student studies chemistry is 15 over 20 equals 1 over 4. What is the probability that a student studies neither subjects? It's 3 out of 20. And finally, what's the probability that a student studies only chemistry? That means only this value, so it's going to be 8 out of 20. Yes, indeed, and 8 out of 20 equals 2 over 5. Now, in the unit with Venn diagrams, we sometimes put parentheses for these numbers to say that it's a number of elements. It's not the number 8 that is here, it's the number of students. When it's not confusing, like here, I think we really don't need to use parentheses. So that's it for 14J. 14K is a bit longer and certainly more demanding. We are going to use the addition law of probability and the law of conditional probabilities to solve problems. So additional law of probabilities, I say here as seen in exercise 7 of the previous section, but given that we are doing this with a screencast, we haven't seen exercise 7 yet. But here's the idea for the addition law. If you are looking for the probability of A or B, remember from Venn diagrams that this is the union of A and B. It is the probability of A plus the probability of B. But what happened here? We took the intersection twice. The intersection is here, and we took it again here. So because of that, we need to subtract the intersection once. So this is the additional law of probabilities. The probability of A union B equals the probability of A plus the probability of B minus the probability of A intersection B. The exercise below here is going to be a simple application of this formula. We know that an event A has a probability of 60% of happening. We also know that the union of A and B has a probability of 70% of happening. The probability of the intersection is 0.3, 30%. What is the probability of B? So it would be wrong to think that, oh, if A union B is 0.7 and A is 0.6, that B is 0.1, because they may have an intersection. And yes, indeed, they do. So we're just going to apply this formula directly. P of A union B is 0.7. P of A is 0.6, P of B is what we're looking for, and P of A intersection B is 0.3. So once we have all these numbers, it's simple arithmetic to find that P of B equals 0.4. Event B has a 40% chance of happening. Now we'll go with a definition. Two events A and B are mutually exclusive if they can never occur together. What it means is, in a Venn diagram, you would have two circles, A and B, which have no intersection. They're completely separate. For example, to be a senior and to be a junior. There's no way you can be both, so they would be separate. And so what's the probability that both are happening? What's the probability that you're a senior and you're a junior? It's 0. There's no chance that this could happen. What's the probability that you're a junior or you're a senior? Now this is going to be both probabilities added. It's the probability that you're a senior plus the probability that you're a junior. And of course, there's a 0% chance that you are both a senior and a junior. So now a notation. Suppose we have two events A and B. Then this writing here, P of A given B, is used to represent A occurs knowing that B has occurred. So this is quite a subtle concept. It means we know that something happened, and given that extra information, what is the probability that A will happen? So we are assuming B happened. What is the probability that A will happen? Here's an example. In a class of 15 students, 10 like pizza and 8 like iced coffee. Of course, some students like both. One student likes neither. If a student is selected at random, what is the probability that he or she likes pizza? This is a basic example that doesn't involve the new concept that I just introduced. So what's the probability that a randomly selected student likes pizza? There's 10 people who like pizza out of 15, so it's going to be 10 over 15. Question B, though, requires more work. What is the probability that a randomly selected student likes pizza given that they like iced coffee? So we have an extra information here. If we know that student likes iced coffee, how does that influence the probability that they will like pizza? And to do that, we want to make a Venn diagram. So one student likes neither. It's not very easy here to figure out these numbers, but you need to find a way for this and this to add up to 10, because there's 10 students who like pizza. This and that should add up to 8, because there's 8 students who like iced coffee, and all together it should add up to 15. But once you passed this difficulty, which we worked on in the Venn diagram unit, you can answer question B. What's the probability that a randomly chosen student likes pizza, given that he or she likes iced coffee? And now we can see there are 8 students who like iced coffee. What is the probability that they like pizza? 4 out of these 8 like pizza. So there's 4 chances out of 8. Question A was very easy, the standard way we learned. Question B, what is the probability that the student likes pizza given that we know that they like iced coffee? And there's 4 out of 8, so 50% chance. So we can write this with a formula, and it looks like that. What is the probability that someone likes pizza if we know that they like iced coffee? It's the intersection of pizza and iced coffee. We saw that was 4 in our previous example, divided by the probability that they like iced coffee. There were 8 who liked iced coffee. So basically we could write 4 out of 15 divided by 8 out of 15, and that would give us 4 out of 8. So the last example here is going to be quite interesting, and if we don't know this new tool of conditional probabilities, it can be very difficult to solve. So in this exercise we have 2 bins, and each of them contains red and white tickets. Bin A contains 3 red and 2 white tickets. Bin B contains 4 red and 1 white ticket. What happens is we take a die, and we throw the die. The die has 4 faces marked with an A and 2 faces marked with a B. And when it falls on an A, we'll choose a ticket from bin A. If it falls on a B, then we'll take a ticket from bin B. So quite a complicated situation. What is the probability that the ticket is red? For doing this, the best strategy is to use a tree diagram. Here is a tree diagram. It's not super easy to read, but what is the chance that we will get to draw from bin A? There's 4 chances out of 6 because we're rolling a die which has 4 sides A and 2 sides B. So 2 chances out of 6 of going to bin B. Now, if we go to bin A, there are 3 red tickets out of 5 and 2 white tickets out of 5. So the probabilities here are 3 out of 5, 2 out of 5. If we were to draw a ticket from bin B, there are 4 chances out of 5 that we will get a red ticket, and only 1 chance out of 5 that we will get a white ticket. So I wrote 4 over 5 and 1 over 5. So question A is what we practiced in a previous section. What is the probability, if I go through this process, that I will get a red ticket? I need to follow all the branches that reach R for red. So it's going to be 4 over 6 times 3 over 5, plus the other option, which is 2 over 6 times 4 over 5. These are the 2 branches I can follow to reach a red ticket. So this is the calculation, and it simplifies to 20 over 30, and therefore 2 over 3, or 66.67%. Question B is the tricky one, and that's the new one. Let's say that you see someone holding a red ticket, and you ask a backward question. Your question is, knowing that this person got a red ticket, what is the chance that that person got it from bin B? So what is the chance, if I know a person got a red ticket, that he took or she took this trajectory rather than this one? So it's a conditional probability because you know something extra. You know that the ticket is red. So we will use this formula here. What is the probability that we took a ticket from bin B knowing that it's a red ticket? So the probability of both going through bin B and getting a red ticket is representing by this branch, bin B, 2 over 6 times 4 over 5. And we have to divide this by the probability of getting a red ticket. Now, what's the general probability of getting a red ticket? It's what we calculated in step A. We found earlier that the probability of getting a red ticket is 2 chances out of 3. So we will divide by 2 over 3, and if you calculate this, it simplifies to 2 over 5, which is 40%. That's really strong, I find. If someone has a red ticket, you know there's 40% chance they got it from bin B. There's 60% chance they got it from bin A. So that's it. Just by the way, sometimes in exercises, we will not ask you question A, we will ask you question B directly. So it's going to be work for you to figure out how to find this or that probability. And as you notice, you are not told that you have to draw a tree diagram. You can use another tool. We saw many tools, two-dimensional grids, Venn diagrams, etc. Just listing cases. You have to choose the best tool depending on the situation. Anyway, that's it. I hope it helped and that you could copy all the notes, and now you should do the exercises for these two sections. Thank you.